right, second video, AP Stat. Tonight we're going to be doing the one proportion z-test, but first I need to introduce you to phantoms. This is going to be our new acronym. So when you're going to be performing a hypothesis test, we will now remember to use phantoms, all right? And that's an easy way to help you remember all the components that you need to include within your significance test or your hypothesis test. First being the parameter, same idea as when we did a confidence interval. Both P's represent parameter there. The H now represents the hypotheses. So you need to state both the null and the alternative right after you do the parameter there. So first it should be what parameter you're talking about. Tonight we're going to be talking about P, which is the true proportion, and our P are going to be included within the hypotheses. So we'll have the null hypotheses being P equals something, whereas the alternative may be P is less than something, P is greater than something, or P can be simply not equal to something. The ACE is still the same for the hypothesis testing, so assumptions. These are going to be the same exact assumptions as your confidence interval assumptions. So if you're struggling trying to keep track of all those, this is great because they're just going to be the same exact thing from when we did chapter 8. We're going to now use the name of the test instead of naming the interval for our N for phantoms. So we're now going to name the test. Tonight's test is going to be a one proportion z-test. We're going to compute now for T the test statistic. Now this will be either the t-score or the z-score. Since tonight's test is going to be a one proportion z-test, we're going to be using the z-statistic, and we're going to talk about that on the next slide. We're going to obtain our p-value for the O part of phantoms. So this is using either normal CDF or t-CDF to obtain said probability, and you're going to now make your decision. So that's when you're either going to reject or fail to reject HO. Remember, if the P is low, the Ho's got to go, all right? So just remember that, and it'll help you make your decision. And then for the last part there, the statement in context. So this is when we're going to say that our p-value is either greater than alpha and we fail to reject, or P is less than alpha and we are going to reject our null hypothesis, our HO. Two statistics here for these hypothesis tests. So we have a Z versus a T. Remember that we will use Z statistics for proportions, whereas we will use the T statistics for means. So remember, those are completely different statistics for completely different tests because proportions are completely different from means, all right? So please make sure that you start realizing the differences between the two tests. We were going to recall the use of the T statistic for means because we oftentimes don't know sigma. So sigma is unknown. So remember, that's always why we use the T distribution over the normal curve for doing hypothesis testing and using it for confidence intervals. So remember that this test statistic is going to be on your formula sheet. This is on the very back page of it, and the test statistic is always computed the same exact way. Except I spelled parameter wrong. Parameter seems to be a thing. So make sure you change the parameter thing here. It should not be parameter. It should be parameter. Oops. Right? But it should be computed as the statistics minus the parameter over the standard deviation of the statistic. Now, and there's two cases of this, all right? So when we talk about our Z statistic, this is going to be the form there. So the form is going to be our p hat minus the p divided by the square root of pq over n. Now this should seem very familiar from our sample distributions of sample proportions. It's the same exact kind of setup, and it's how you're going to compute your Z statistic here. For your T statistic, very similar, except that sigma is unknown, so we're going to use S of x to estimate, so it should be x bar minus mu divided by S of x divided by the square root of n. So please make sure that you write these separately and make sure that you know that Z statistics are going to be for proportions. So oftentimes we're going to use this for doing our one prop Z test. And here we're going to be doing this for our one sample T test, and that'll be in following videos to come. All right, so for the one proportion Z test here, all right, what we're going to do is we're going to use that Z statistic. So make sure that you have that p hat minus p divided by the square root of pq over n. So that's going to be how we're going to compute that test statistic, that T part of phantoms, all right? So again, the conditions here should be very similar. We're going to take a simple random sample, a random sample, or a random assignment of treatments and use that to verify the random condition. Now, it is very, very important here that if it says simple random sample, you designate it as so. But if the problem just says a random sample, then you don't need to say it's a simple random sample. Just because something is a random sample doesn't always mean it's a simple random sample. Normality needs to be met. Remember that we do NP and NQ are both greater than or equal to 10. We do need to make sure we follow this up with the statement here about the sampling distribution. This was lacking on a lot of their tests when we did the 1 proportion Z interval, and I would like to see that improve. So remember that once we meet these conditions, once we meet this NP and NQ are greater than or equal to 10, we're now going to talk about the sampling distribution of p hat being approximately normal due to there being at least 10 successes and 10 failures, okay? In our calculator, you need to probably write this down. We're going to use the 1 proportion Z test in the calculator, which is going to be under stat and tests going to number 5 in order to figure this out. And there's a cool button that you can actually use to draw the normal curve and then shade it. And then you can copy that down. So we'll go over that when we do an example in just a moment there. All right, so our first example here is going to be talking about a potato chip producer. So this producer has just received a truckload of potatoes from its main supplier. So if the producer here determines that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load from the supplier. All right, so that's pretty significant there. So if we have more than 8% that have these blemishes, so if more than 8% have the blemishes, we're going to send a truck away. So the supervisor selects a random sample. Notice it does not say simple random sample, so do not designate it as so on your assumptions check when we do our hypothesis test. It's just a random sample of 500 potatoes from the truck. An inspection reveals that only 47 have these blemishes, okay? So we have 47 that have the blemishes, okay? Carry out a significant test at the alpha level, which is 0.05. Remember, we talked about that being the balance point there. We don't want our alpha level to be too low or too high. We kind of want it right in the middle, and we'll expand on that in the unit to come here. So, but let's try to see what we're going to do about making the decision about this truckload of potatoes. So if more than 8% have blemishes, we're going to send it away. So we took a sample here. All right. So a couple things that we need to know is that our p hat is going to be composed of looking at out of 500 how many had blemishes, and that should be apparent that 47 there do have those blemishes. All right, which means that our p that we're going to be using is we're going to be using the 8% to represent the population proportion, because if 8% have it, that's going to be okay, but we're interested when it's more than, okay? So that's the claim that we were talking about in our video earlier this week, okay? So let's go ahead and do the phantoms procedure. We're going to start with the parameter part. So starting with the parameter part, they're saying that we want to now not estimate anymore. We're going to test this claim. So this is the big change there. We want to test the following hypotheses at the alpha equals 0.05 significance level, where our p is going to be the true proportion of potatoes in the shipment with blemishes. So we have that, right? Hypotheses there. So we're going to state our two hypotheses here. So our hypothesis should be p is going to be equal to 0.08, and our alternative. Now I went quickly through this because the alternative is very clear. So from the previous slide, we knew that we were talking about more than 8%. So more than 8% in the shipment have blemishes. We're going to have issues. All right. So here we're going to let that p be greater than 0.08 for our alternative hypothesis there. So for the alternative, we're going to the p is greater than 0.08. All right. We're going to state our assumptions. So we have a random sample of 500 potatoes from the shipment. So we use that random sample to determine if we're going to accept or reject this truckload. All right, we do need to check for normality. So we do have 40 potatoes, okay? So using 0.08 times 500. So we expect to see about 40 potatoes have blemishes if 0.08 is the true proportion there, okay? Which means that we expect to have 460 failures. So 460 potatoes that don't have blemishes there, all right? So we already see that we're about 7 over what we expect in terms of blemishes. So let's see if that's going to be significant enough. Since we both have successes greater than 10 and failures greater than 10, we're going to be able to say that that sampling distribution of p hat is approximately normal, all right? So this is us doing the background work here in terms of trying to figure out can we go through with this hypothesis test? And the answer is yes, because our assumptions have been checked. All right, and we know that we are looking for evidence to see if that proportion is greater than 0.08. All right, so remember that our test tonight is going to be the one proportion z-test. So doing a one proportion z-test means that our test statistic here should be a z-score. So we have z is going to be equal to p hat minus p divided by the square root of pq over n. Now from the previous page in the problem, right, we're going to need to start plugging in the values of p hat, p, q, and our sample size n. All right. So on the next little part here, I've kind of charted that for you so it's going to be easy to kind of plug in stuff. So remember, a p hat is going to be the 47, and it shouldn't be over not 600, but it should be 500. So that is a small error there. So it should be 500. So 47 over 500, which is 0.094. And our p-value, or our p, which is our true proportion, is going to be 0.08. All right, so we're going to go ahead and plug all this in. So remember, our sample proportion goes first. Subtract out our population proportion, which is 0.08. And we're going to divide by PQ over N. Remember, when we have P, we're going to use it. So we're going to use it as 0.08, and its complement is 0.92. Divide that by the sample size, take the square root, and it should give you a Z statistic of 1.15, right? So we're now going to try to obtain our p-value. So remember that we're interested to see the proportion of those above, I guess the observations above 1.15 standard deviations above the mean there. So using our normal CDF of 1.15 to infinity 0.1 if you want to use the z-score. I know some of you guys still don't like doing that, so I put the other normal CDF that you could use. So you can put in the sample proportion of 0.094 going to infinity, and then having the mean of p hat, which is going to be p, which is 0.08, go in there for the mean, and then I calculated the square root of pq divided by n, and that gives you 0.0121. You can also see how I'm going to do this in the calculator, and I'm going to show you that now. All right, now we should see that we're going to get the p value of 0.1251. So remember that there's a lot of p's here. We have a p that represents the population proportion, we have a p hat that represents the sample proportion, and we have a p value, which is a probability of observing this p hat and compared it to its true proportion p. Right, so 0.1251, well, that's not low enough to make the hoe go away. So we're going to make our decision here, and since our p-value is actually greater than our significance level of 0.05, we're going to fail to reject the null hypothesis. So we're going to fail to reject the hoe. All right, which means that in our statement in context, we're going to need to talk about, since our p-value is greater than alpha, we fail to reject HO. Right? There is not convincing evidence to prove that the shipment contains more than 8% of blemished potatoes. So even though that expected number was 47, which actually was 40 compared to 47, 47 potatoes is not significantly higher than 40 in this case. So basically that 47 falls within the acceptable ranges of blemished potatoes. So we don't have enough evidence to say that the shipment contains more than 8%. So we need something higher than 47, maybe like 54, 57 may do that. But 47 is not that enough. So what we're going to do here as a result is that the producer should use this truckload, because since more than 8% don't have blemishes, this truckload's okay to use. All right. So, and if they don't, then you're going to run into some issues where, you know, you're sending back a good truckload of potatoes, and that's going to cost money, and there's going to cost issues. And we'll talk about what the consequences of that would be if you mistakenly reject or fail to reject. All right. That is going to be the end of our video this time. So hopefully you guys enjoyed it. Be sure to rewind if you need to go over any of the parts there, but try to keep it short, sweet, and to the point. We'll see you in class tomorrow.